Last time we started section 4.3 and we completely finished and covered greatest common multiples, right? We talked about the fact that greatest common multiples are in fact smaller, most of the time smaller, never bigger than the number themselves. And then the other section that other thing we're going to talk about in this section is least common divisors. And we mentioned last time that least common divisors are actually bigger than the values that we're working with. At least as big as, but bigger most of the time. So let's jump over here into the least common divisor part. Definition. I said least common divisor. I meant least common multiple. I'm sorry. Oh, it's going to be one of those days. Let's just hope it's not. All right, least common multiple. The least common multiple is the least non-zero whole number that is a multiple of all the whole numbers in your set. And that's kind of what some of your problems in the last section were having you do, wasn't it? You were writing out lists of multiples, and you were looking for where things coincided. Those are common multiples. And the least common multiple is the smallest one. And just like in the last section, there are several ways to do this type of a problem. The first one is called the number line, or sometimes called the colored rods method. So what we do is we show multiples of all the numbers on a number line in intervals of each value, and then we find the first value at which the intervals coincide. I'll talk about the colored rods part in the description here in a second. All right, so here's how this works. Find the least common multiple using colored rods. I'm going to do the number line part of this first.
Can we go back? I didn't get to.
Yep.
We can have a binder check today.
It'll be next week.
Okay.
Yeah, it'll be next week. All right, so our numbers are 6 and 15. Okay? Did you still need it to coincide?
I couldn't find the page for like.
Oh, okay, gotcha. All right. Anyone else? Okay, 6 and 15. All right, a number line method means actually having a number line and marking off the multiples of each of your numbers. So one of the benefits of this is that it's very visual. We will start with the 6. So here is the first multiple of 6. It's 6. What would be the second multiple of 6? 12. And then we'd get 18. And then we'd get 24. And then we'd get 30. And I'm going to stop because 30 is my answer and I've run out of space anyway. I know, it's a bum. Okay, so the idea is that if I were to, and I'll do this because I have the ability technology-wise to show you. If I were to sort of, one of the ways that you've probably heard this called before is skip count. Has anybody heard of skip count? Their book doesn't talk about skip counting. But you guys have skip counted before because you've all done this. 2, 4, 6, 8, 10, 12. You've done that, right? That's skip counting by 2s. 3, 6, 9, 12, 15. That's skip counting by 3s. So if we're counting by 6s, oh man, that is a one big arrow. That's a little bit better. These would be skip counts by 6s. So if you go from one multiple of 6 to the next, these are skip counts of 6s. We can also do skip counts of 15s. So if I were marking this number line and I were going lengths of 15, the first mark would be, of course, at 15. The second mark would be at 30. And in terms of my skip counting, my number would start at 0 and it would go to 15. And then it would start at 15 and it would go to 30. And then the answer is actually the first place where they both end on the same value. So this is my answer. It would be 30. So I'm using colors to do this just because I'm on the board where I have the ability to use the colors. But let me show you what this actually looks like with what are called colored rods as well. Okay, so my answer to the least common multiple of 6 and 15 is in fact 30. 30. Okay, colored rods are an actual manipulative. Like you can use them in the class, the kids can touch and feel them. And they're really cool because what they do is they have one color for each type of a length. So everything that would have whatever we would call as length 2 are all the same color, and everything that has length 3 are all the same color. So it's like having Legos or whatever, but they don't stick together. They're just rods. They're blocks, okay? And they can stack end to end. So visually, they very much look like what I'm about to draw, in theory. We're going to let ours, because we don't have any reason not to let them be, we're going to have our 6s have length or have blue colors. So these would all be, it's not good, length 6. And they're actual physical blocks, okay? So I know mine don't look perfectly all the same, but if you were working with this in a classroom, you'd actually have physical objects and they would, in fact, all be exactly the same. And you just line them up end to end, okay? So these are blocks lined up end to end. They all have length 6. And then you would have blocks lined up of the other length. In this case, the one we're looking at on this one is actually 15. So you have blocks of length 15. So this block has length 15. And you can see that it doesn't end at exactly the same location that blue blocks ended when they were put side by side. So on your next one, you would stick it end to end. And all of a sudden, lo and behold, stuck end to end appropriately with these blocks, it now does end exactly at the same place as the blue blocks when they were lined up end to end. Okay? And then on the blocks, different manipulatives will do different things. It'll actually have the length and the number and so forth. And you can talk about the fact that 15 plus 15 is 30, right? So the answer would be 30. So those are the colored rods that go along with them. Okay, so this is very visual, very colorful, very kinesthetic learners, right? They can touch and they can feel, and that's all really good. It has limitations, obviously, especially if you're really using the physical manipulatives that you touch and feel, because they don't have every length known to man, right? It's not going to work. And so there are some limitations with it, but it's starting out, you know, in terms of actually what you're looking at and working with, it's a good way to start. So let's go on to another method that maybe has a little bit more of a future to it. And there's a limited future to that last method. Intersection of sets. An intersection of sets method is where we list out multiples of each value, and then we find the least value that the lists have in common. It's usable. It kind of beckons to our sense of multiplication tables because I'm going to write out the list of multiples like on a multiplication table list. If the numbers are quite large, it might not be something that you have memorized, maybe a drawback, right? And if the numbers don't coincide for a long enough period of time, your students are probably going to be angry with you, right? So we're going to do an example with 12 and 15. So our goal is to make a list of multiples. So if I'm starting with 12, the first number in the list will be 12. And then I need to find what 12, that's 12 times 1. What is 12 times 2? 24. And 12 times 3? 36. Now at some point you might be thinking, I don't want to multiply 12 times that number. Well, just take the previous number and add 12 to it. That works too, right? So 36 plus 12 is 48 plus 12 is 60 plus 12 is 72. I'll write one more. Plus 12 is 84. Okay, so this keeps going forever, right? So there's no end in sight. There's no end ever to this list. We do the same thing with the number 15, and we hope as we're doing it that at some point we come across a number that's in common so I don't have to go back up to that ... and fill in more lists, right? More list. Start with 15. What's next? 30. 45. 60, and I get a stop. Why? They have something in common, don't they? Okay, that was really large. Let's try that again. 60, first number in common in both lists. So what that tells us is that the least common multiple of 12 and 15 is 60. One good check step on any of these would be to make sure that it really is a multiple of both numbers. In other words, if you take 60 and you divide by 12, does it actually give you a whole number? If you take 60 and divide by 15, does it actually give you a whole number? It's a good check step. It doesn't answer the question completely, but at least it tells you it is a multiple. So it's one way to check for reasonability of your answer. Okay, so like I said, this is not especially friendly if the list went on forever, right? If you had the numbers 14 and 15, this would not be pretty. 12 and 15 wasn't so bad. So let's try something where the number of things is maybe a little bit more workable. The next method is called prime factorization method, and we had this name of this method before with the greatest common divisors. We also have it with least common multiples. We construct the prime factorization of each number, and then we choose all prime factors in each factorization. We list those prime numbers with the largest exponent. That's different. Last time we used the word smallest there for greatest common divisors. And then on step 4, we write the product of the values from number 3. All right, so my example actually has 3 numbers in it, which is fine. We have 90, 50, and 20. So what we're supposed to do is we're supposed to find the prime factorization of 90, 50, and 20. And I'll do 90 with my division tree, and then I'll do the next one with the factor tree. So this division tree, smallest number it divides by is 2. And 90 goes into 2 how many times? I didn't say that right.
45.
2 goes into 90 how many times? Yes, 45. What's the next prime number?
5.
It's actually 3 before we get to the 5.
Do we have to do it like that?
Technically, if it's telling you on the paper to do this with this particular algorithm, then yes.
So, okay.
But it doesn't on this one. So if you went out of order, on this one, would it matter? And the answer is no. Yeah. So this would then be 15, where you'd get another 3, and then you'd get that same 5. So this one is 2 times 3 squared times 5. Enough of you don't like this method, so I'm going to use the factor tree too to show you that I am versatile. 50 divides by what? 5 and 10 is probably the numbers you're going to go with. 10 divides by what? 2 and 5. Have I gotten down to primes everywhere?
Yes.
Yes, there are 3 primes here. It's 2 times 5 squared. The last number is 20. We'll do a factor tree on that one as well. This one could be written as 4 times 5, and 4 would then be written as 2 times 2. So I have 2, 2, and 5. So this is 2 squared times 5. Now, here's where the difference lies. All of that's the same as what we did last time. We just wrote down prime factorizations. When we were looking for greatest common divisor, we were looking for the primes they had in common, correct? For least common multiple, we're not looking for what they have in common. We're just looking for anything that's there ever in any portion of any of the numbers. So we're going to list all of the primes. So what's the smallest prime that you see in any of these lists? We have 3 lists. We have a 2. We'll get the numbers, we'll get the exponent on it in a minute. What's another number that's in any of the lists?
3.
3. What's another number that's in any of the lists? 5. Are there any other numbers, prime numbers, as bases in our lists? No. The next thing that we do is we look for the largest exponent instead of the smallest. So it's 2. Which one has the largest exponent?
2 squared.
That one right there, right? 2 squared. What is the largest exponent of 3's? Yeah, it's in the first number. It's 3 squared. And the largest exponent of 5's? 2. It's in the middle one, actually. There's a 2. Yeah, 5 squared. So they don't always give factors that have 2's. I mean, they're not always 2's, okay? But this one they happen to be. Your last step is to actually multiply these out. So you can write it in there in your calculator like that. You can change this to 4 times 9 times 25. Whatever it takes. Eventually you will end up with, looks like 900. So your least common multiple of 90, 50, and 20 is 900.
So, like, if you had, like, say in another problem, or like, even in this problem, say if you had like a 2 to the 3rd, then you also had a 2 to the 4th, you would use the 4.
You would. Yes, whichever one is the biggest, that's when the one you would
every
use.
specific number. Not
Exactly.
Like overall.
On each individual different number. Okay. Let you fill in the blanks on the next one, then we'll talk about it and do the problem next time. Okay, but then blanks are at least all filled in. So division by primes, we write the numbers in a row. You divide each of the numbers by a common prime factor. You divide all the quotients by a common prime factor. Any factor that divides at least two of them. Let's see. Not simply relisted, yeah. We repeat step 3 until no other common factor can be found. And the least common multiple is a product of the primes in step 4. So let me say 2 more comments, or maybe 3 or whatever I end up with before you. We're not going to do the example, but we did division by primes before, right? Yes. Division by primes looks and feels a bit like the prime factorization, but they all go on the same row. The difference between this one and the division by primes before is there's 2 differences, actually. One of them is that if any number divides at least 2 of the numbers, so if you have 3 or 4 or 5 numbers, but it divides at least 2 of them, you can put the number on the outside and you can do the division. And I'll show you how it affects the other numbers it doesn't divide, but you can do the division. The second difference is on the answer for greatest common divisor, the only part of the answer was the numbers that divided evenly into everything, right? For least common multiple, it's going to be those numbers times everything else that's left over that doesn't have anything else in common. So the number is going to be bigger than you started with, right? Okay, we'll pick up with an example of that next time.